Hello and welcome to another supplementary video on rhombuses. In this case we're going to be asking the question, if we are given the two diagonal perpendicular bisectors, can we find the angles? Okay, so before we go on with our proof of how to find the angles, I need to first of all prove that these lengths AC and BD, which we already know by now are perpendicular bisectors, we need to prove that they're also angular bisectors. That is to say, they chop their angles exactly in two. So are the diagonals of a rhombus angular bisectors as well as perpendicular bisectors? Well, in order to do that, let's take one of the angles at random. I'm going to pick this angle here, which I've labelled A, and I'm going to say that the first part of this angle here, which I'm trying to point an arrow to, I'm going to call it alpha, because I like my Greek alphabet at the moment. And then this other half I'm going to call beta. Now if they're both halves, exactly halves of this angle, then we can say that alpha is equal to beta, because they're both the same size, because they're both exactly half of this angle A. Now if both diagonals are indeed perpendicular bisectors, then this angle here, which I'm calling D, I can split that up into an angle which I'm going to call gamma and an angle which I'm going to call delta. And then I can also say that gamma, if I can draw gamma, is equal to delta. Okay, so to prove that, I'm going to try and prove that I'm going to use another colour, and I'm going to show you that this is a right angled triangle here. So I'm going to show you that this triangle is the same as this triangle. And if I can prove that this triangle, that the blue triangle is exactly the same as this, whatever colour it is, I think it looks a bit orangey to my eyes. So if this blue triangle is the same as this orange triangle, then the angle here, which I've labelled alpha, must be the same as the angle here that I've labelled beta. Okay, so let's go about finding a way of proving it. Well, the first thing is this line here, AB, is exactly the same as this line AD, because they're both legs of a rhombus, and therefore, because all the lengths of a rhombus are exactly the same, so line AB must be the same as line AD. Now we can also say that this line BE is the same as the line ED, because we know that the diagonals of a rhombus are perpendicular bisectors, that is to say they cut each other exactly in half. Therefore BE and ED are both exactly the same length and both exactly half of length BD. So we've now shown that this length is the same as this length, and we've shown that this length is the same as this length. And now all we need to do is show that this line AE is the same for both triangles. Well, that's obvious because line AE is shared by both triangles. So this length's also the same, so AE is also the same. So all three lengths are exactly the same for both the blue and the orange triangles, and therefore the two triangles are congruent by the side-side-side proof of congruence, and therefore angle alpha is indeed equal to angle beta, and therefore exactly half of A. So we can prove at least that this one diagonal AC is an angular bisector. But what about this line BD? Is that also an angular bisector? Well, what we're going to want to do now is pick another colour. I'm going to pick red. I'm going to show that this red triangle here is the same as this orange triangle. Well, again, this length here is the same as this length here. That is to say, length AD is the same length as length DC, because they are both sides of a rhombus, and all four sides of a rhombus are exactly the same. Now this length ED is shared by both triangles, and therefore this length is also exactly the same for both triangles. And we can say that length AE is the same as length EC, because we know that length BD is a perpendicular bisector. That is to say, it chops length AC exactly in half. So AE is equal to EC, which are both exactly half of length AC. And therefore, again, by side-side-side proof, we can say that these red triangle and the orange triangle are both exactly the same. And therefore, angle gamma is indeed equal to angle delta, which we said was the conditions that we would need to prove to show that length BD and length AC are both angular bisectors. That is to say, they chop their angles in two equal halves. Okay, so we've got our rhombus and we've got our two diagonals, which are our perpendicular bisectors, P1 and P2. But what if it's the angles that we want to find? Well, again, we can observe that we've got a right-angled triangle. I'm going to draw it in blue, I think. That doesn't work very well, so let's see if I can highlight it. So we've got our right-angled triangle here. Now these diagonals, they cut the angle exactly in two. So this angle, if we call this angle here, if we call it, say, theta, then this angle, that's part of it that's been cut in two, is just theta over 2. In fact, let's give it another name. Let's pick one. If we're going with the Greek alphabet, let's call it alpha. So alpha is equal to theta over 2. Just for fun, you know. Okay, so we've got our angle here, which we're calling alpha. So alpha is equal to, well, if this is the angle and this is a right angle here, let's pick another colour. Then this length here, I want a nice thick line so you can see it. This length here is the opposite . So this is the opposite. And then this length here, I'm going to highlight it. This length here is the adjacent. And what do we know about opposite over adjacent? Is tan theta. Well, in this case it's tan alpha. So if I say tan alpha is equal to opposite over adjacent, well, the opposite is our P2 divided by 2. and that has to be over the adjacent, which is P1 divided by 2. Okay, so that's a bit ugly. Is there anything we can do to simplify this? Well, what if we times top and bottom of P2 over 2 over P1 over 2 by 2? We can times by 2 over 2 because that won't change the value, because 2 over 2 is just 1 and anything times by 1 is itself. So we can say tan alpha is just equal to P2 over P1. So alpha is equal to the arctan, or the inverse tan, of P2 over P1. And now we've got our angle. Well, we've got half our angle anyway, because we remember alpha is equal to theta over 2. So theta is equal to twice the tangent P2 over P1. So that's our one angle here. So what are the other angles in the quadrilateral? Well, we know the opposite angle is just going to be theta. It's the same angle. Opposite angles are identical, so this is just going to be theta as well. And then this angle, because adjacent angles are supplementary, is just going to be 180 degrees minus theta. And then because this angle here is opposite, this is also going to be 180 degrees minus theta. And there we have it. We have our angles given just our perpendicular bisectors. Okay, I hope you found that helpful. If you liked the video, don't forget to like, comment and subscribe. If you're taking your GCSEs this year, I'd like to wish you all the best with your revision and all the best with your exams. And I look forward to seeing you in another video.